Hello everyone, welcome to this video. In this video we'll be looking at another result which states that we have when can we have the subgroup which is generated by a to the power I equal to a to the power j, right? And when can we say that the order of a to the power I is equal to the order of a to the power j, right? So the result here, this tells us that if suppose the order of some element a is equal to n, so that means we are in some group G. From this group we are taking one element which is a, and we are saying that the order of this element is equal to n, right? So here in this case we are saying that the subgroup which is generated by a to the power I is equal to the subgroup which is generated by a to the power j if and only if the GCD of n with I is equal to the GCD of n with j, and the order of the element a raised to power I is equal to the element a to the power j if and only if the GCD of n with I is equal to the GCD of n with j. So that means we have to prove both ways in both the results, right? So let's proceed with the first result here. For the first result we wanted to show that if this thing is true, that the subgroup generated by a to the power I is equal to the subgroup generated by a to the power j, then these two GCDs, they are equal to each other. Now according to the theorem that we have already studied, right? So using this theorem here and using this part of this theorem, we know the subgroup which is generated by a to the power k could be written as the subgroup which is generated by a raised to power the GCD of n with k, where n is the order of the element a. So therefore, the subgroup which is generated by a to the power I is equal to the subgroup which is generated by a to the power GCD of n with I, right? And similarly, the subgroup which is generated by a to the power j is equal to the subgroup which is generated by a to the power GCD of n with j, right? According to the above theorem. So that means here we have to prove that if these two things, they are equal to each other, then their GCDs are also equal. So that means we have to prove that the subgroup which is generated by a to the power GCD of n with I, if this is equal to the subgroup that is generated by a to the power GCD of n with j, then both the GCDs, GCD of n with I and the GCD of n with j, they are equal to each other, correct? So let's see how we can proceed here. So in one part of this proof is quite obvious. If both the GCDs, they are equal to each other, then this quantity is same as this quantity. So therefore they have to be equal to each other. So one part is obvious. Now let's see the opposite. So that means if we say that both of them, they are equal to each other, then the GCDs, are they equal to each other? If yes, how? So let's see, we assume that both of them, they are equal to each other. So what would this imply? This would imply, now according to this result that we have studied, that the order of element is equal to the order of the subgroup which is generated by that element. So from here you see we have the subgroup that is generated here, they are equal to each other. So that means their orders are also equal to each other. If their orders are equal to each other, so that means they are equal to the order of the element itself, and they are equal to each other, right? So the order of a to the power GCD of n with I is equal to the order of a to the power GCD of n with j. So according to the following theorem, we now have, because we now have this thing that the order of a to the power k, that is equal to n divided by the GCD of n with k, right? So here we have the order of this element. So according to this element could be written like this, n divided by the GCD of n with I, and this element is written like this, that it is n divided by the GCD of n with j. So from these two equations we would obtain that the GCD of n with I is equal to GCD of n with j, and this is what we wanted to prove here in this part. For the next part of the theorem here, we wanted to prove that if the order of a to the power I is equal to the order of a to the power j, then both their GCDs, they are equal to each other, and vice versa. So let's see the result here. Now because we are assuming that both of them, they are equal to each other, so that means here according to this previous theorem, we can apply this result, and according to this result we have n divided by GCD of n with I is equal to n divided by GCD of n with j. So this gives us GCD of n with I is equal to GCD of n with j, and we can proceed in this manner by reversing the steps. So both ways the result is true, hence we say the result is proved, right? So I hope you understood this result. Well, that is it for this video. Thank you for watching.